from the planet's most stunning state-of-the-art structures.
We are 64 meters below sea level.
Look at this super tower, 632 meters tall.
To its mightiest modern machines.
This plane is huge. This plane is the largest passenger aircraft in the world.
The thing that makes the maglev very different from your everyday train is the speed at which it travels and it floats.
None would have been possible without the groundbreaking innovators of the past.
I never realized that it's so beautiful, so slender.
I don't think without the L we would have had this great, vibrant American city that we have today.
It was really quite a daring feat of engineering.
In this episode, a ship of record-breaking proportions.
There is nobody in the UK who has ever built an aircraft carrier or a ship of this size.
Its cutting-edge naval and aerial engineering.
We're actually going to execute the shipborne rolling vertical landing.
And the pioneering historic designs.
We often talk about the bravery of the pilots, but actually, you know, they must have been slightly crazy as well.
I do love this airplane.
That made the impossible possible.
This is what most engineers dream of.
July 2014, Scotland. The largest and most powerful warship in the history of the British Royal Navy is being floated for the first time.
If you look in history in terms of all the massive projects British engineering's done, this has to be up there as one of the most complex and challenging ones.
The Queen Elizabeth aircraft carrier is at the vanguard of naval engineering. The most sophisticated ship ever built in the UK. At 65,000 tons, the $4.9 billion vessel dwarfs its predecessors. And for engineer Stuart Justice, this giant piece of impossible engineering is a once-in-a-lifetime project.
When I first started, the sense of scale was absolutely awesome. It's around 280 metres long and has 4 acres of sovereign UK territory that can be deployed anywhere around the world.
The Queen Elizabeth has a range of 10,000 nautical miles and can carry up to 40 aircraft, including the groundbreaking F-35B Lightning fighter jets. Some of the world's strongest marine gas turbines provide the muscle to drive this mighty floating airport and act as an onboard power station, generating enough electricity to power the equivalent of a large town.
I think when you're standing up here, you get a really good view of the absolute sheer scale of this project, and just the sheer size of the flight deck in HMS Queen Elizabeth is awe-inspiring.
The Queen Elizabeth will be the flagship of a nation with the proudest of naval traditions and enable Britain to undertake major military or humanitarian missions in all 4 corners of the Earth. But little more than a century ago, it was an engineering feat inconceivable, let alone possible. Once upon a time, the effect of a nation's navy was limited to what it could achieve on water alone, either fighting at sea, firing onto land from the water, or delivering an invading force. It wasn't until the mid-19th century that the first attempts to combine sea and air power were made using balloons. In 1849, an Austrian ship attempted the first attack, launching a hot air balloon to drop bombs on Venice. The mission failed, however, when the wind changed. It would take the development of an exciting new type of flying machine before the impossible dream of a proper aircraft carrier could be realized. The seaplane would be the catalyst for a revolution in naval engineering.
Oh, that is so cool.
Dr. Rhys Morgan is taking to the air to get a taste of the challenges the early aircraft carrier pioneers faced.
The birth of the aircraft carrier depended on the skill of the pilots and the creativity of the engineers. But what we recognise as aircraft carriers today are a long way from the early ideas.
The first carriers were literally just that. Simple transporters of seaplanes, which would crane them on and off the water for deployment from the sea itself. Frustratingly slow and highly risky.
Those early seaplanes were very flimsy. They were made from wood and fabric, and the sea conditions made it terrible for the pilots. Taking off in rough seas must have been incredibly difficult. We often talk about the bravery of the pilots, but actually, you know, they must have been slightly crazy as well.
It was clear a new technique would need to be devised. And in 1912, British pilot Charles Sampson would first attempt the seemingly impossible: to launch his seaplane from a battleship that was under steam.
It was Lieutenant Charles Sampson who first attempted to take off from a moving ship. And of course, using the principles of engineering, understanding the principles of flight, it was actually very beneficial to have a moving ship, because the ship was already creating airflow over the wings, and that creates lift.
Lieutenant Sampson used a specially adapted battleship with a perilously short sloping runway fitted on its foredeck. And on the 9th of May 1912, with the ship steaming forwards into the wind to maximise wing lift, he fired up his engine and his flimsy seaplane trundled down the ramp and then skyward.
Now, these early aircraft carriers only had about 30 metres of takeoff deck, so it's an extraordinary feat to get the plane off the ship and into the air.
But these early versions of aircraft carriers had one major disadvantage. There was nowhere on board to land. So the planes were quick to deploy, but still slow and dangerous to recover.
As we come into land, it's going to be incredibly bumpy, but nothing like the kind of conditions that it would have been for some of those early seaplane pilots out in the English Channel and the North Sea.
But within a few years, one man would change the face of naval aviation forever. In 1918, shipbuilder William Beardmore creates HMS Argus, the first genuine aircraft carrier. It was the original ship to use a single flight deck, allowing aircraft to both take off and land on the same floating runway. Argus was fitted with an ingenious retractable pilot house in the middle of the runway, which would be lowered out of sight during flying operations. It meant the ship's air force could be deployed and recovered at great speed, making the aircraft carrier a truly effective weapon for the very first time in history.
William Beardmore's continuous flight deck set the template for all modern aircraft carriers.
HMS Argus had achieved the impossible. The new Queen Elizabeth class carrier may owe a debt to William Beardmore's Argus, but it's taken the concept to a whole new level. Elizabeth is almost twice as long and 3 times wider than the Argus.
The aircraft carrier has an absolutely massive flight deck. You could actually park 80 London double-decker buses.
At 16,000 square metres, it's a vast surface area, the equivalent of more than 2 football pitches.
HMS Queen Elizabeth and our sister ship, HMS Prince of Wales, are the largest ships ever built for the Royal Navy. At 65,000 tonnes, they represent a 3-fold increase on our previous class of aircraft carrier, the Invincible class.
But in order to create this floating Goliath, the engineers were faced with another seemingly impossible problem.
No one company within the UK had the capability to be able to actually design and construct the aircraft carrier.
So how could this monster feat of impossible engineering actually be accomplished? The solution. 3 different companies would form a groundbreaking collaboration, using 6 shipyards and over 100 different suppliers around the UK. Work begins on the Queen Elizabeth in 2008 and requires enormous manpower.
At the moment, we have around about 3,000 people working on the HMS Queen Elizabeth here in Rosyth. And across the UK, we have 10,000 people.
The method of construction will be unique. Manufacturers the length and breadth of the country are each required to construct self-contained sections of the ship, complete with cabins, corridors and pipework. Even key mechanical components are pre-installed in these units, including the ship's huge diesel generators. The sections are then transported by barge for assembly in the giant dry dock in Rosyth, Scotland.
It's essentially putting together a very, very large jigsaw puzzle.
However, using this radical new building technique means added pressure for the engineers. If the sections of the ship are to join exactly, every element must be perfect. And in June 2012, it's the moment of truth.
In terms of the engineering precision, we've had to design the interfaces between each of the blocks to millimetre accuracy to ensure that when we line them all up, all the pipes come together and all the penetrations for cables and other things are all in the right place. You're thinking how all the engineering we've done going to ensure that these blocks come together well. And yes, they did. This is the first time any ship of this scale has been assembled from multiple different yards.
But in creating this ultra-modern flagship for the British Navy, its builders still face major challenges and will have to draw on innovations from the past.
If they got hit, they would literally explode. Being a skipper on that boat was like riding a bomb.
To produce more impossible engineering.
Wow.
The Queen Elizabeth-class aircraft carrier is the next generation of warship and the largest vessel in the British Navy's illustrious history.
It puts the Royal Navy very much back into the Premier League of navies around the world.
The mega carrier is 280 metres long and 3 times the size of Britain's previous aircraft carriers. But in creating a ship this immense, the engineers have set themselves a seemingly impossible challenge. How to give it enough muscle to cut through the world's oceans at the speeds required to launch its fleet of jets. This mighty vessel will need a monster motor to move it.
You can see here just the sheer scale and size of these engines. Everything on the Queen Elizabeth-class aircraft carrier is large, but the engines themselves are an absolutely immense piece of engineering.
And the ship's designers will again look to the innovators of the past to make powering the colossal carrier possible. Early man had to rely on elbow grease to push him across the water, until he learned to harness the power of the wind. It wasn't until the early 1800s that engineers discovered steam could provide a mechanical solution. And another 100 years before diesel engines began to rule the waves. But come the 1940s, a brand new technology was on the horizon. During World War II, engine power became a matter of life and death. And one boat above all others embraced the need for speed.
This boat is absolutely gorgeous. It's so sleek. It's like a shark going through the water. And you can understand, just looking at it, why they called it the Spitfire of the sea.
Britain's motor gunboats led the way in high-speed naval combat. And thanks to a dedicated team of enthusiasts, MGB 81, built in 1942, is the only one still running today.
It was an incredibly well-designed boat, beautifully engineered. It had these incredible engines. It had 3 V12 Packard engines. These each had a brake horsepower of 1,250 pph. That's equivalent to 6 Formula One engines. And this was in the Second World War. It's just unbelievable. It's just starting to take off now. Look at it go. These boats used incredible amounts of fuel. They had to carry 10 tons, and it was high-octane fuel. It was aviation fuel. If they got hit, they would literally explode. Being a skipper on that boat was like riding a bomb. The reason they needed these huge engines was because the boat was made of mahogany. It must have weighed a ton. It would be like your granny's wardrobe. This boat is idling at the moment. We're still trying to keep pace. Hello there. You've got a beautiful ship here.
Yeah, we're stopping wet.
They needed this huge engine capacity because they needed to get up to a ship, drop some depth charges, and then get the hell out as fast as they could.
Packed with armaments and heavy fuel, MGB 81 could still go a staggering 50 miles an hour through the water.
Wow, you can see it bow wave just crashing over there.
But fast as it was, in 1947, another motor gunboat would go even further.
Down to the Solent in the wake of new progress at sea. Jets take the water.
Motor gunboat 2009 would herald an engineering revolution on the high seas by using a propulsion system that gave it unparalleled power: the gas turbine.
The gas turbine works through a series of stages. It first sucks in air through the fans at the front, and then a series of compressors squeeze that air, increasing the pressure, and then it mixes the air with a steady stream of highly explosive fuel, and then combusts that fuel-air mixture. And that explosion generates very, very hot gases. And those gases shoot out the back of the engine, turning these turbine blades. And these turbine blades drive a shaft connected to the propeller.
MGB 2009 was the first naval vessel in the world to be fitted with the system. And the innovation was big news.
MG 2009 is a triple-screw, 110-foot craft featuring a compressor turbine that enables the engine to develop and maintain greater power than in any other ship of comparable size afloat.
The gunboat 2009 was a piece of impossible engineering that has now become commonplace, with everything from naval vessels to cruise ships making use of the power of the gas turbine. The gas turbines employed on the Queen Elizabeth aircraft carrier, however, moved the technology pioneered in the 1940s to a whole new level.
We're on the second deck level of the gas turbine space. So the gas turbine is that large, it actually takes up over 2 entire decks of the aircraft carrier.
With a turbine system this immense, Just the installation is a feat of engineering in itself.
Because of the size, we have to install gas turbine and its alternator set on the deck below and then lower the top section of the ship on top of it.
The Queen Elizabeth is powered by 2 Rolls-Royce MT-30 gas turbines, the world's most power-dense marine turbines. But unlike their predecessor in the 1940s motor gunboat, these turbines aren't used to directly turn the Queen Elizabeth's propellers. Instead, they act like a giant turbocharger to generate huge power boosts to drive the ship's electric motors at key times.
The ship can operate normally with the diesel generators for essentially what we call cruising speed. The aircraft carrier weighs around 65,000 tonnes, so when we have to go to higher speed for flying operations, we then employ the gas turbines and the gas turbine alternators to give us that speed through the water.
And in combination with the ship's 4 huge diesel generators, these gas turbines have another vital job.
So with the 2 gas turbines and the diesel generators, what we have in essence is a mini power station. It just doesn't provide propulsion, it provides power for the ship's crew. So it provides the ability to be able to heat the ship, the ability to cool the ship when it's in the tropical climes, and provide power throughout the operation of the ship.
But when crafting a 21st century aircraft carrier, the ship itself is only half the story.
I do love this airplane.
And the Queen Elizabeth's designers will need to look to history's great aerial innovators to again make the impossible possible. The Queen Elizabeth-class aircraft carrier is the largest warship ever produced in the United Kingdom. The same length as London's Houses of Parliament and as tall as Niagara Falls. But creating this most modern of aircraft carriers is not only about building the ship itself. The aircraft deployed by it are integral to the whole package. And the 2 entities are being developed in tandem to create one awe-inspiring engineering feat. The ship is designed in harmony with the new US Lockheed Martin F-35B, the most advanced short takeoff and vertical landing aircraft in history. The F-35B has a top speed of over 1,200 miles per hour, is virtually undetectable by radar, and is stunningly responsive to its pilot's will.
The step change in technology of the F-35B is absolutely immense.
The Joint Strike Fighters will launch using a system unique to British carriers, affectionately known as the ski jump.
The F-35B will start its takeoff at the other end of the flight deck and accelerate along the flight deck and then go up the ramp. And as it's going up the ramp, it provides vertical lift and allow the aircraft to take off from the top of the ramp. The ski jump ramp gives us the capability to launch and recover aircraft at a very high sortie generation rate, which is the ability to be launching a large number of aircraft into the sky.
The cutting-edge F-35B, combined with state-of-the-art aircraft carrier design, will make the Queen Elizabeth unrivaled in its capabilities. But without the pioneers of the past, this extraordinary fusion would be literally impossible. Post-World War II, as propeller-driven planes made way for faster, more powerful and heavier jets, runways had to grow much longer. But there are obvious limits to how long a runway on a ship can practically be. Airships could be deployed from a small deck space, but the slow and unwieldy blimps would be no good for modern military use. Helicopters, first mass-produced in the 1940s, allowed vertical takeoff and landing. But there's a limit to how fast they can travel before the forces exerted on the rotors take their toll. The perfect solution would be a fast fighter that could take off and land on a sixpence. Some of the first experiments fell somewhere between helicopter and plane. The American-designed Convair Pogo was a propeller-driven plane designed to take off and land balancing on its tail.
Okay, John, give her a little power. Pick her up a little more. Keep her up. Keep your nose up. Bring her down, John. Atta boy. Okay.
But the British had a very different idea.
While Americans experiment with aircraft which take off standing on their tails, Britain pins her hopes on an evolution of the flying bedstead.
The flying bedstead was the affectionate nickname given to the thrust-measuring rig, championed by brilliant engineer Dr. Alan Griffith. And it first took to the air untethered in 1954, causing a sensation.
Films of the fabulous flying bedstead. The whisper of this extraordinary new flying machine reached us about 5 months ago. Designed for experiments in vertical takeoff, the bedstead has 2 jet engines mounted end to end. Their exhausts shoot the blast downwards and thus give the machine its upward thrust.
Alan Griffith's pioneering experiments would inspire the development in the 1960s of an engineering triumph and probably the most revolutionary aircraft of all time. The Harrier Jump Jet. Former US fighter pilot Art Nels has the only privately owned Harrier flying in the world today.
The Harrier was revolutionary because it was the first operational airplane to successfully vector thrust. That gave it what we call vertical short takeoff and landing capability, or VSTOL.
I do love this airplane.
Art's love affair with Harriers has lasted 35 years, ever since the moment he was first taken for a flight in one as a rookie.
He slammed the power forward, threw me back in the seat. The acceleration was unbelievable. He brought it into the hover, and after we landed, I just went, this airplane can do anything. When do I start?
The Harrier's unique capabilities are down to its radical design. The aircraft has one central engine with large intakes either side of the cockpit. Its amazing maneuverability is down to the 4 adjustable nozzles along its fuselage. These can direct thrust whichever way the pilot desires, allowing the 7-ton jet aircraft to be able to hover and even fly backwards. It's the Harrier's seemingly gravity-defying properties that enable a new generation of aircraft carriers to operate in a way that would once have been impossible.
Harriers operating from smaller aircraft carriers are actually force multipliers. A Harrier could operate from the forward half of the ship, and helicopters could operate from the stern of the ship, essentially as if it were 2 separate runways.
As revolutionary as the Harrier jump jet was, the air arm of the new Queen Elizabeth takes carrier firepower to a whole new level. And in order to create the perfect conditions for the F-35Bs, the engineers have employed some equally futuristic technology. Pilots have been running test flights in a highly advanced simulator system, so they can perfect both aircraft and ship design while they're still under construction.
The Queen Elizabeth, it's a marvel of engineering and it's a magnificent aircraft carrier, but without the aircraft, it's pretty much nothing. It has to interact with the aircraft seamlessly. And so through this simulator, we're able to allow the aircraft to take off, land, maneuver, approach in all sea states, all conditions, and check that the systems all work and interact correctly. It actually is a very comprehensive representation of operating from the ship. It's not only the aircraft cockpit, but it's also the control tower on the ship as well.
The multi-million-dollar simulator allows the pilots and engineers to reduce the potential hazards that go hand in hand with running a mobile airfield at sea.
It's possibly the only landing point you can execute a safe landing on for hundreds of miles. And although it's very big, it's not that big. It's maybe a tenth the size of a conventional runway for a military fast jet base. And although it's a marvel of engineering, it's only one small point, and it can be difficult to find.
Working in harmony, the pilots and engineers have devised flying methods for the high-tech 35Bs that will be unique to the British carrier.
The bread and butter landing will be the vertical landing, and that will be familiar to Harrier pilots of old. But the difference between the Harrier and the F-35 is, for us in the UK, we're actually going to execute the shipborne rolling vertical landing, which is a landing with a certain degree of forward speed, which allows us to carry more fuel and more stores back to the ship.
The combination of the lift generated by the wings and the lift from the downward thrusting engines enables a slower approach speed and means the F-35Bs can land using very little runway.
As I touch down, apply the brakes, and then come to a stop.
Both the technological innovations and the assembly of the Queen Elizabeth are major feats of engineering. But to complete this 21st century warship, the designers still face massive challenges and will again have to draw on the pioneers of the past.
So we embark on building the largest naval force the world has ever seen,
to create even more impossible engineering. Britannia may have historically ruled the waves, but in 2014, a new aircraft carrier launched in Scotland dwarfs any ship the British Navy has owned. 280 meters long and weighing 65,000 tons, it's a feat of engineering once thought impossible.
It's only really when you're in the dock bottom that you understand the real size of the Queen Elizabeth class aircraft carriers.
But the Queen Elizabeth is not only the largest warship ever produced in the UK, it's also one of the most innovative in the world. And for engineer Stuart Justice, it's a dream project.
For myself personally, this represents the pinnacle of my career. To be able to say to your children and grandchildren that you've worked on the nation's flagships.
Even below the carrier's expansive flight deck, the scale of the construction is immense.
The hangar deck, in terms of engineering, is a feat within itself. It's that large, you could actually put two Type 23 frigates fully within here in the hangar deck, side by side.
At 155 meters long by 33 meters wide, the hangar may be spacious enough to fit two whole ships inside, but it's perfectly proportioned for its real job, stowing the carrier's aircraft, be they fighter jets or helicopters. But the Queen Elizabeth's immense storage space presents engineers with another seemingly impossible challenge. How to get the carrier's array of very heavy flying machines from the hangar and into the air at the speeds required for modern warfare.
It's very, very important to be able to transition from having the aircraft here stowed in the hangar deck up to the flight deck, put a large number of aircraft in the sky very, very quickly.
The Queen Elizabeth team will need to look to the innovations of the past to make the impossible possible. While the British might have led the way in terms of the early carriers, it took an American design to crack it, and along the way turn aircraft carriers into the new kings of the naval jungle. The Essex class of aircraft carriers, like the USS Intrepid, have been described as the most significant warships in American naval history. They were an innovation driven by the advent of the Second World War.
The key thing to keep in mind is Europe's already at war. France surrenders to Hitler. We're still at peace, but the United States becomes very worried. So we embark on building the largest naval force the world has ever seen.
When the US was thrust into the war by the Japanese carrier-led attacks on Pearl Harbor, the importance of these mighty ships was thrown into sharp focus.
As we get to the period past Pearl Harbor, a carrier goes from the up-and-coming new vessel out there to being the dominant vessel at sea. So as we build less battleships, we start building more carriers, and this is our ultimate carrier design of the period.
This ultimate aircraft carrier exploited all the lessons learned from the early ships and supersized carriers for the first time. The Essex class is over 60 feet longer and more than a third heavier than its predecessor.
The key difference with the Essex class in terms of the flight deck is that it's larger. When we look at the earlier carriers the United States had built, for the most part, they had slightly smaller dimensions, reflecting the fact that when they're designed in the 30s, we're talking about lighter aircraft, in some cases still biplanes. So you need larger space for these aircraft to launch. You want to launch more aircraft on a major strike.
With this larger, heavier flight group, designers of the Essex class faced the same challenge the engineers on today's Queen Elizabeth now face: how to get planes from hangar to runway at high speed.
A big innovation that allows for that is one of the elevators being moved off to the side, sticking off from the flight deck. This is going to take less space away for the elevators.
The Essex class popularized a brand new engineering solution. An aircraft elevator on the side of the deck would allow planes to be lifted from the hangars below and onto the flight deck without interfering with flying operations. And the new ships were so well engineered that they became history's most prolific aircraft carrier design.
Ultimately, they complete 26 of them, 17 during the Second World War. Intrepid is the third of the Essex class.
Despite often coming under heavy enemy attack, not one Essex-class carrier was ever sunk. They had made the impossible possible. Now, the engineers of the Queen Elizabeth aircraft carrier are taking the same concept of a deck-edge elevator and applying it to the Royal Navy's largest ever warship.
These aircraft lift are incredibly powerful. They can lift the entire ship's company of around 1,600 people from here on the hangar deck all the way to the flight deck.
But lifting power on this scale would be impossible without another of history's great engineering innovators. Born in 1810, William George Armstrong began life as a lawyer, but switched careers to become one of the world's most eminent engineers, inventing a simple concept that changed the world of engineering forever: the hydraulic accumulator. Armstrong realized that by placing a weighted piston on top of a cylinder of water, he could store hydraulic energy. Whenever power was required, for example, to open a bridge, it could be instantly released in a highly controlled way. His inspired design would be used for one of history's most iconic landmarks, London's Tower Bridge, where stored hydraulic energy would be used to make way for tall ships passing along the River Thames. Engineers on Queen Elizabeth have exploited Armstrong's genius to lift massive loads at high speed. The powerful system will take around 1 minute to raise aircraft from the hangar to the flight deck.
The chains that raise and lower the aircraft lift are operated by hydraulics. So we'll have a large amount of hydraulic pipework within the structure behind here, which then control the raising and lowering of the aircraft lifts.
all of which would be impossible without Armstrong's principle of the hydraulic accumulator.
We can see down here the aperture for the forward aircraft lift, which is down currently at the hangar deck level, and then can transition up with two fully laden F-35s up to the flight deck level to allow the aircraft then to move out onto the flight deck to take off on the ski jump ramp at the front.
It may have been inspired by engineering of the past, but the Queen Elizabeth also contained some never-seen-before features. Until now, all carriers have had a very familiar profile. A large flight deck and single tall superstructure known as the island. But the Queen Elizabeth is going one better. Instead of having a lone island, this mega carrier will have two, each with its own specific function. The fore island will be the nerve center for all ship operations, and the aft will handle everything to do with the aircraft.
The Queen Elizabeth class aircraft carrier is unique in terms of having a twin island design, and each island has got its own unique purpose. The aft island is predominantly used for aircraft operations. From the aft island, you can see the approach for the aircraft coming into land. You can see the entire flight deck looking along the entire runway up into the ski jump ramp at the front as well. And here on the forward island, this is where all the navigation's done and where the ship's steered from.
These two massive superstructures must also be built off-site and floated to the dock in Rosyth for installation. In March 2013, the feat of impossible engineering begins. The fore island, all 595 tons of it, is craned into position. For the first time, turning the huge floating hull into a recognizable aircraft carrier. And 3 months later, the aft island follows and produces a carrier with a profile unlike any other in history.
It's the first aircraft carrier in the world to have this sort of configuration. So having two islands is very much a British innovation.
It's now more than a century since man took his first tentative, pioneering steps towards creating the phenomena of the aircraft carrier. Now, by drawing on the innovations of the past, adapting, improving them, and making groundbreaking innovations of their own, the engineers, designers, and every one of the 10,000 workers involved in the construction of the Queen Elizabeth class carriers have succeeded in making the impossible possible.